Well, good morning and welcome to the webinar today. My name is Carrie Berger and I'm the coordinator for the Northwest Fire Science Consortium. For those of you not familiar with the consortium, we are one of 15 fire science exchange networks that are funded by the Joint Fire Science Program. In 2017 alone, over 12,000 science delivery activities were completed by the exchange network, including workshops, field tours, research briefs, and multimedia productions with more than 400,000 participants. So to learn more about the consortium or to sign up for our monthly newsletter, visit our webpage at northwestfirescience.org. To avoid any noise interference, I have muted your audio, so if you have a question, please go ahead and type that into the chat box. Also, I will be recording the webinar and will archive it on our website and YouTube channels, and you can find both those web addresses in the chat window. So Brooke Cassell is joining us today. Brooke is a research assistant at Portland State University. She recently completed her PhD using modeling to understand long-term forest and wildfire dynamics in the Inland West under alternative management scenarios. She is interested in linking ecological and social perspectives toward the development of applied solutions for ecological questions. So Brooke, whenever you're ready, it's all yours.
Thanks, Carrie, and thank you so much, everyone, for coming. I'm really excited to be here today to be able to talk about some of the research that I've been working on. So today I'm going to be talking to you about my research into fuel treatment effectiveness in the southern Blue Mountains of Oregon. And I just wanted to give you a quick overview of the larger project. So this is just one part of a much larger project called Outcomes Prioritization on Fuel Treatment Placement in Extreme Fire Weather in 3 collaborative forest landscape restoration project landscapes. So this is a JFSP funded project, so thank you so much, JFSP. And I just wanted to give a quick shout out to the project partners on this. Louise Loudermilk is with the U.S. Forest Service, and she's the PI on this overarching project. Also, Robert Scheller and Matthew Hurteau are co-PIs on the project, and Dan Crosscheck is a postdoc working on the project. And so I wanted to let you know that he has a few publications out already that if you are interested in this kind of research are great to check out. They just came out this past year. So this project has an overarching goal of looking at several different landscapes across the United States that are very different in terms of forest structure and composition, and also fire regime, in trying to identify priorities for placing fuel treatments on these landscapes that are different and also that have similarities. And so the 3 landscapes are the Malheur National Forest in the Blue Mountains of Oregon, which is the project I'm working on. And then there's also research going on right now in the Osceola National Forest in the Florida Panhandle, and results from the Dinky Creek landscape came out last year, which are those publications by Dan. So if you're interested, definitely check those out. So first I want to touch on the part of the title that talks about extreme fire weather. So why are we interested or concerned about extreme weather? Well, we know that the climate is changing, and it's changing globally, and it's also changing specifically regionally. Globally, the temperatures have risen over 0.5 degrees Celsius from 1880 to 2011, and those temperature increases are only increasing and projected to continue throughout the next century and beyond. And in the western United States, those increases are actually double what they have been globally. So this trend is impacting the United States and especially the western United States. And along with changes in temperature and precipitation, there's also an increase in wildfire activity expected in the western United States. Now, with global climate change, some areas of the world are actually expected to have lower wildfire activity, but in this part of the world, we're expected to have greater wildfire activity. And why might this be? Well, with temperature increases, there is also an increase in what we call the fire season. So the season or period of time in which fires typically occur is lengthening, and this is in part due to those increases in temperatures It's also due to increases in the number of consecutive dry days, changes in the number of hot nights, as well as changes in patterns of precipitation. So global climate models project changes in precipitation in some cases, perhaps increases in precipitation, in other cases decreases in precipitation. But one trend, especially for this part of the globe, is more precipitation falling as rain instead of falling as snow, which results in lower snowpack and earlier spring melt, which contributes to the lengthening of the fire season. So with changes in climate, we do see changes in wildfire activity, and in our case, more wildfire activity. What we've seen over the last 3 decades is actually a tripling in the amount of annual acreage burned, and at the same time, we've seen a tripling in the amount of money that's been spent on wildfire suppression. Now, why is this important? Well, last year alone, in 2017, the Forest Service spent nearly $2.5 billion on wildfire suppression alone. Now, that does not even include money spent on preventative measures. It doesn't include losses due to private property lost, natural resource losses, and ecosystem services related to those natural resources. So this is a big impact, not only on the people who live in these landscapes and are directly affected by wildfire, but also to federal budgets. So thinking about smart ways of spending that money are becoming more and more important. Now, zooming in even closer into the western United States, wildfire is a big part of our lives out here. For those of you who live in this region, you know that this past year was a pretty active wildfire year, and it's not the first. And in the inland Northwest especially, where fire suppression has led to changes in the fire regime and changes in fuel beds, we're seeing a large increase in wildfire activity. Now, fire suppression, being in effect mostly over the last century, has led to changes in fuel beds that are on the landscape. So what you see here is a picture from the Canyon Creek fire in 2015. This was a big fire in the Malheur National Forest, larger than average, certainly. But what you see here is a landscape that is dominated by ponderosa pine, which is a fire-adapted species. But there's also an encroachment of species that are not fire-adapted, like white fir and grand fir, and greater numbers than we would have expected to see in the past. So this landscape that in the past experienced much more low intensity, low severity fires that happened more frequently, is now experiencing fires that are larger and more severe and with more mortality. And with a greater number of people moving into these forested areas in the inland west, we are more and more worried about wildfire occurring in these forests and how to deal with them and how to prepare for them. Speaking of fuels, I wanted to just touch really quickly on the fire behavior triangle to talk about, well, what is it that we can affect when thinking about wildfire in these types of ecosystems? So the wildfire behavior triangle has 3 legs. So the first is topography. Now, topography is going to affect wildfire behavior based on slope or aspect of the landscape where the fire is occurring. But wildfire behavior like intensity and flame length are also impacted, of course, by climate or by weather, as we talked about a little bit earlier. So changes in temperature and precipitation are important in driving more intense fire behavior. But another important aspect of weather is wind. So with stronger winds and changes in wind direction, that can also change the behavior of a wildfire. But the third leg is fuel. And this is the leg that we really have any control over in being able to change fire behavior. And fuel affects wildfire behavior based on the kind of fuel it is, the species of vegetation that's present, and also the arrangement and the continuity of those fuels. So are those fuels widely spaced? Are the fuels made up of large trees with thick bark that are resistant to fire and have spaces in between them, or are they highly continuous? Are they right next to each other? And is there also vertical continuity where fire can go from the forest floor and travel through shrubs and small trees up into the canopy of the forest, where it becomes a much more severe fire with higher mortality? So fuels are the one area of fire behavior that we really have any ability to make any changes. So one of the bases for this study is thinking about the fact that fuel treatments are a widely used and well-established method for affecting wildfire behavior when fires occur. So there's a large body of literature and tons of evidence that fuel treatments work at the stand scale. So fuel treatments work by reducing fire spread intensity and severity by modifying the forest structure and modifying the fuel bed structure to reduce the continuity of fuels and to alter the composition of what species are present on the landscape to favor species that are more fire resilient or more fire resistant. So by proxy, fuel treatments also reduce fire suppression costs because it will be easier to put fires out, or because fires won't spread as quickly or as extensively. So I just wanted to touch on 3 different types of fuel treatments that are frequently used. The first is light or pre-commercial thinning. So this type of thinning is typically done with small diameter trees, trees that are probably not very commercially viable, but it's done to reduce those small fuels that are both horizontally and vertically continuous to reduce fire spread. The next type of treatment I just want to touch on is more of a heavy treatment, heavy thinning or commercial harvest. And this type of treatment is removing larger diameter trees. So it can target commercially valuable trees. And in effect, it can quote unquote help to pay for the treatment. So this type of treatment can include it can include clear cutting, but typically in the inland west, clear cutting is less likely to be the type of treatment that's used, and more of a seed tree or shelter wood treatment. It's more likely where sources of seed for natural regeneration are still present on the site. Nevertheless, this type of treatment, as you can see in this example photo, reduces the fuel load to the point where fires are likely to drop to the ground and be much more easy to control. And then the third type of treatment I want to touch on is prescribed burning. And prescribed burning has been shown to be very effective at reducing fuels, especially when it's used in conjunction with either of the first 2 types of treatment. So either being used after a pre-commercial thinning or a commercial harvest to reduce the slash from those treatments, and also to reduce fuel loadings in terms of shrubs and small diameter trees. But it's also been shown to be effective on its own without being joined with one of the other types of treatments, as long as the site that's selected is selected carefully. So prescribed burning also reintroduces some of the benefits of fire onto the landscape that are absent when fire suppression keeps those fires from accessing the landscape. So species that are actually maintained by fire, ecologically important species that are maintained by fire, can benefit from prescribed fire, as well as nutrient cycling that's affected by prescribed fire. So it's not a full surrogate for natural fire, but it can be beneficial both to the ecosystem and in terms of fuel reduction. But of course, if a treatment is going to be effective in reducing wildfire activity, a wildfire needs to encounter it, right? And not only does a wildfire need to hit that treatment, it needs to intersect it during the effective lifespan of the treatment. And depending on the forest type and the fuel type, that can be as little as 1 to 2 decades. And so some studies have looked at, well, what is the likelihood that a fuel treatment will be encountered by a wildfire within that time span? a study by Barnett et al. They looked at all treatments on federal lands across the entire United States and looked at the likelihood that wildfires, or looked at the rate at which wildfires intersected those treatments within a 15-year time period. And they found a pretty low rate, about 6.8%, and in some western forests, it's even lower than that. So it really begs the question. We know that fuel treatments are effective at the stand level, but what about at the landscape level? What is the likelihood that these treatments are making an impact when we look at our treatment prescriptions across the entire landscape? And what about over long periods of time? Because we know that decisions that are made in forests now will affect wildfire behavior and forest structure and composition into the future. So thinking about fuel treatments at these large landscape scales and at long periods of time, can we increase the likelihood of fires intersecting treatments? Is there a way for us to optimize treatment placement and potentially be more efficient in placing treatments across the landscape to be more likely to actually affect landscape level wildfire severity and wildfire spread? So these questions are difficult to answer since we don't have a crystal ball and we can't look into the future. But what we do have are landscape models. And landscape models, when carefully calibrated and carefully used, and done so with the knowledge that all models are faulty, but some of them can be very helpful. When keeping those things in mind, a landscape model, such as the model used in this study, Landis-2, can help us answer these questions about long time frames and large landscapes. So Landis-2, just a little bit of background about Landis-2, it is an exceptional model because it includes a lot of complexity. And so the questions that you're able to answer or ask through using Landis-2 can be fairly complex. So drawing your attention to the squares on the left side of the slide, the type of data that we input into Landis-2 are things like vegetation data, current vegetation data, climate data such as daily weather on the particular landscape of interest, soils data that relates to soil moisture, and also topography can be input into this dynamic landscape model. And drawing your attention more to the right side of the slide, oh, I forgot I have a pointer here. Yes, okay. So looking more at the right side of the slide here, looking at the concept of how this model works to answer these types of questions. And it is a spatially dynamic landscape. So within each site on the landscape, all of that data from the left-hand side, the vegetation data, the climate data, all this data is input at the site or the ecoregion level. And then processes such as tree mortality, competition, regeneration, and growth are all simulated within the sites on the landscape. And then they're also simulated across sites. So for instance, seeds can disperse from one site to another, and therefore species can march across the landscape and regenerate in cells where they didn't previously exist. And this also goes with disturbance. Landis allows a whole suite of disturbances to be simulated, and the disturbance in this study is wildfire, but there are many other disturbances that can be simulated through Landis. And the disturbances are driven by and interact with those forest dynamics. And then we also can implement management on the landscape. And management can include commercial harvest, pre-commercial thinning, and can also include prescribed fire. So this was the perfect model to be able to use for this particular study and answer these kinds of questions about treatment placement and effectiveness. And I already told you that my portion of the study is looking at the inland west in Oregon, and the study area is indicated in the dark black line and includes the southern portion of the Malheur National Forest, as well as a small portion of the Wallowa-Whitman National Forest. This area was really interesting for this particular study in part because it crosses ownership boundaries. The wildfire doesn't care who owns or who manages the land. So for this study, we included areas that are privately owned as well as that are managed by agencies. Now, the area in the lighter green color is the Forest Service land that is manageable. So in other words, not wilderness and not roadless areas. Those are areas that are actually managed by the Forest Service. And that makes up the bulk of the manageable area, although some other agencies like BLM, Oregon State, and Bureau of Indian Affairs are also managing parts of this landscape. And you can see in the pink there that the Collaborative Forest Landscape Restoration Program is in the central part of this study area, which makes this area also a great place to do this study because there is a lot of management happening. And so simulating management that's currently happening on the landscape and the Accelerated Restoration Program was helpful in being able to define what management looks like. Also interesting about this landscape is that it contains a variety of different forest types and therefore different fuel types. The outer portion of the landscape that's in a lighter brown color, you can see, is primarily juniper woodlands, shrublands, and grasslands. So these were included because even though most of our questions are about forest in this study, those ecosystems carry fire quite readily and will carry fire from outside federal lands into federal lands and vice versa. The predominant forest type on this landscape is ponderosa pine and dry mixed conifer. But there are also pockets, especially in higher elevations and on north-facing slopes, of moist mixed conifer forest, lodgepole pine forest, and also high elevation forest that has species that are more fire sensitive, like subalpine fir and whitebark pine, areas that are more likely to burn at high intensity and have high severity and would be expected to have lower frequency of fire. However, this is a very fire-prone landscape. It historically has been, and it continues to be. A recent study by James Johnston showed a mean fire return interval between 10 and 28 years across forest types. So that included not only the dry mixed conifer forest, but also moist mixed conifer forest and high elevation forest. So historically, this is a very fire-prone landscape and continues to be so. Over the last 15 years, there's been an average of 1.6 fires per year. So there continues to be quite a bit of fire on the landscape. And these fires are increasing in their size as well as in their severity. And this picture I took when I went to look at the Canyon Creek fire after it was out. And what you can see here is a mixed severity fire with patches of high severity, patches of low severity, and patches of mixed severity. So this is maybe not a typical fire for the area, but it's one that happened pretty recently. So to understand the landscape level effectiveness of fuel treatments, I wanted to compare a couple different kinds of scenarios. So I first looked at contemporary weather and then also looked at extreme weather, quite a few different treatment types, and then also spatial placement of those treatment types. And I'll go into the description of those just a bit here for you. So for contemporary weather, I used 32 years of daily data. And for extreme weather, I wanted to represent realistic weather that has occurred that we can expect to have occurring more frequently due to climate change. And so I drew daily data from years that had high fire activity. So 1990, 2007, 2014, and 2015 were all years with a lot of fire activity. And so for my extreme weather scenario, I just used a distribution of weather, precipitation, temperature, and of course wind speed and wind direction, which are very important in fire behavior, just from those years. Now, I know we have some forest managers in the group, so I wanted to give you a description of the management scenarios just briefly, and I'm happy to take additional questions later on them. But I started with an untreated landscape, no treatment, which was the control group. And then I looked at the business as usual management scenario. Now, I met with forest managers at the Forest Service. So this is silviculturists and fuel managers, and developed the closest kind of management that I could within the constraints of the modeling in order to emulate what kind of management is being done on the ground right now. And so the management strategy for business as usual was to favor ponderosa pine and western larch fire resilient species, and implement about 1% of the landscape treated per year, 10% of the landscape treated every decade, with a combination of pre-commercial thinning, commercial harvest, and prescribed fire. So then, in order to do some comparisons with some more aggressive management strategies, I included riparian areas, which have been identified as potentially carriers of fire from one area to another on the landscape. And this strategy favored broadleaf species on a 50-year rotation and aimed to remove all but the relict conifers, all but the very old conifers. And I used prescribed fire in that as well. And then I used two additional scenarios that increase the amount of prescribed fire on the landscape. And this is increasing prescribed fire on its own, not with mechanical treatments. So for the first of those, I approximately doubled the amount of prescribed fire on the landscape, and for the final scenario, I tripled the amount of prescribed fire on the landscape. Now, to make this a little bit easier as we go, since there are so many scenarios, I decided to give you some little icons. So whenever you see the U.S. Forest Service badge, that is the business as usual scenario. It doesn't actually just include U.S. Forest Service, since there are other agencies involved, as well as some non-industrial private harvest, but that's the icon for business as usual. Now, riparian, I'm afraid to say I did not see any landscape level effects by adding treatments in riparian areas. Now, this doesn't mean that you would not see effects at the stand scale, but at the landscape scale, there was not enough riparian area. It's not a large enough proportion of the landscape to affect the landscape level wildfire behavior and activity, and so I'm not going to go into those results. But I will show you results from the scenario with additional prescribed fire, which is illustrated by an extra drift torch, and tripling the prescribed fire, which is indicated by 3 extra drift torches. So by tripling the amount of prescribed fire in the landscape, the strategy goes from treating about 1% of the forested landscape per year to about 2% of the forested landscape per year. So finally, looking at spatial placement on the landscape, which really gets to the heart of the question about can we spatially optimize these treatments and keep our effectiveness. So to do so, I looked at distributing the treatments across the forested landscape, which is shown here, which is about 1.5 million acres of available forest land for treatment. Then I ran 1,000 simulation years with no treatment to identify the cells on the landscape that are most likely to burn and to burn more frequently than the other sites. So if a site was likely to burn more than once over that period, it gained a higher score than a site that only burned once or didn't burn at all. Next, I looked at high severity. So I tried to identify the locations on the landscape that were most likely to burn with high severity. And in the case of the outputs from this particular model, severity is defined by the potential fraction of the crown that is burned, which is linked with both flame length and potential mortality of the species that are in that wildfire. So I overlaid the frequency of the fire and the likelihood for high severity of fire with the areas on the landscape that are available for treatment based on not being wilderness, not being roadless areas, and created a portion of the landscape for optimizing treatment. So with the idea that consolidating treatments in these locations that constitute about 40% of the original treatment areas, we would be able to reduce costs of treatments and also reduce the extent of the landscape that is being specifically treated for fuel treatments, therefore freeing up those areas for other kinds of management to reach other types of management goals and objectives. So on the distributed landscape and the optimized landscape, and under the 2 different weather scenarios, I simulated 10 replicates of each of those scenarios. And these were simulated over the entire 2.5 million acre landscape And the resolution is worth mentioning that I ran this at a 4-hectare resolution. So meaning that every site on the landscape is simulated at a 4-hectare resolution. So all of the data for that site would be homogeneous across 4 hectares. And that was done in order to identify broad landscape trends. So these questions about fuel treatments, again, are not looking at changing the effectiveness of a fuel treatment within a site, but rather the average effect across the entire landscape and across a 100-year period. So looking through time in order to integrate forest dynamics into these questions. So when fuel treatments were implemented under contemporary weather, which again represents the last 30 years of weather, it was obvious that treating the landscape with a business as usual scenario was certainly effective. There were more fire-free years, so it decreased the average fire-free years from 11 out of 100 to 14, which is a great outcome. It also lowered the average amount of annual area burned. So average area burned went from 25,000 acres per year to 15,000 acres per year on average. And there were also fewer years with extreme wildfire activity. So I looked at years that had over 100,000 acres burned, and over 100 years treating the landscape at a 1% of the forested landscape rate reduced those years from 7 to 3 out of 100. So treating the landscape obviously worked, even under contemporary weather. When we look specifically at annual area burned under contemporary weather, you can see pretty clearly that there is a drop in the annual area burned when you treat the landscape. So just to give you a quick overview of this slide here. So the first box that you see, this blue box, is the untreated landscape. And then the next set in the green is the business as usual scenario, and with the first box being distributed and the second box here being the optimized landscape. So when you're looking at these, they come in pairs, and so the first will be distributed, the second in the pair will be the optimized landscape. So what you can see right away is that treating the landscape, even with business as usual, we see an immediate drop in the annual area burned, but there's not a strong trend, not a strong difference among all of the treatments. So doubling the amount of prescribed fire on the landscape decreased the amount of annual area burned, but it was not a strong trend. And tripling the amount of area of prescribed fire on the landscape did create a statistically detectable drop in annual area burned. There was an effect once you triple the amount of prescribed fire, but doubling the amount of prescribed fire was not sufficient to bring about a big change in annual area burned under contemporary weather. But one thing that I find very interesting is that optimizing those treatments gave similar results to distributing them across the landscape. So by consolidating treatments in those areas that are at highest risk for high severity wildfire, in these cases under contemporary weather, they had a similar effect on reducing annual area burned. But where we really see these treatments and their effectiveness is during extreme weather events. So this is similar to other studies. There's a Loudermilk study in Lake Tahoe that also showed this effect where under extreme wildfire, because there are more chances for wildfires to occur, and those wildfires are spreading at faster rates and therefore hitting larger amounts of the landscape, that treatments are typically more effective because there's a greater chance that those fires will actually hit the treatments. And in this case, that was certainly true. So the first map here is the untreated map at the top that has a great deal more purple. So what you can see is that fire frequency is reduced quite a bit in the bottom 3 maps, which indicate any kind of treatment. So to the left, the business as usual treatment. The middle is doubling prescribed fire, and the right is tripling prescribed fire. And the most interesting outcome related to fire frequency is that there was a 47% increase in fire-free years when prescribed fire was tripled from the business as usual treatment. So prescribed fire did a really good job of decreasing fire frequency or fire incidence on the landscape in any given cell by creating those fire breaks that allowed fires to be suppressed and not to spread to neighboring cells. Moving on and looking at distributing treatments or optimizing treatments, again, what I found is that, and for this example, this is the business as usual treatment strategy, but optimizing treatment resulted in very similar results as distributing treatments across the landscape. And in fact, it increased the fire return interval by 5%. So it was beneficial to optimize those treatments in areas that were at high risk for frequent and severe fire. Looking at annual area burned under extreme weather, we see again that all of the treatments decreased the annual area burned at the landscape scale. And remember, this is averaged across the entire landscape. And the effect of decreasing annual area burned was significant when prescribed fire was tripled. So again, doubling the amount of prescribed fire on the landscape was not sufficient to move that average area, annual area burned from the business as usual scenario, but tripling the prescribed fire was very effective. Now, also interesting, I want to draw your attention to this last box here. This is the optimized treatment scenario for tripling prescribed fire, which you see is only as effective as the business as usual scenario or doubling of prescribed fire. So spatially optimizing those additional prescribed fire treatments was not effective in affecting additional annual area burned. Now, I want to look really quickly at average fire severity as well, because reducing fire severity is one of our objectives with field treatments. What you'll see is that under extreme weather, treating the landscape at all had a significant influence on decreasing average fire severity at the landscape scale. But what you'll also notice is that there's not a big difference among treatments. This is also consistent with previous studies in other landscapes. But what I want you to keep in mind here is, if you look at the asterisk here over prescribed fire, tripling prescribed fire, keep in mind that although average fire severity was not decreased at the landscape scale, there are fewer acres burning annually at these severity levels because of the drastic decrease in annual area burned when prescribed fire is tripled. Looking more spatially with average fire severity, again, you can see here when you're looking at these maps, the lighter colors indicate lower fire severity on the landscape. And so you can see that optimizing the placement of treatments decreased the fire severity in a large portion of the forested parts of the landscape. However, if you look at the circle on the right-hand map where these treatments have been optimized, there are areas of the landscape where that severity increases, of course, because those areas were not treated. But overall, optimizing the spatial placement of these treatments was very effective in reducing overall landscape severity. Looking at increasing prescribed fire, again, in the distributed landscape, you have even greater gains in reducing average landscape level fire severity at a much broader area of the landscape than with the business as usual scenario alone. However, that is averaged out when you optimize the treatments because, again, spatially optimizing the prescribed fire alone treatments was not effective in shifting landscape level fire severity. And you can see why when you look at the map of where fire severity occurred in the southwestern portion of the landscape that was not treated with additional prescribed fire, those benefits were not realized. So what I would like you to take away from this talk there are a few takeaways. The main one, which is fuel treatments not only work at the stand level, but they do work at the landscape level and over long periods of time to reduce wildfire activity under both contemporary and extreme weather, but they are most effective under extreme weather, again, because they're much more likely to intersect with fuel treatments when weather is more extreme. Also, optimizing treatment placement in areas that are more likely to burn more frequently and at high severities, it achieves similar landscape scale reductions in wildfire activity as placing those treatments more widely distributed across the landscape. So the benefits of concentrating treatments could be considered when thinking about prioritizing treatment placement across the landscape without sacrificing reductions to overall landscape fire spread and severity. And finally, more prescribed fire is needed to increase treatment effectiveness, even if that prescribed fire is done on its own and not in conjunction with mechanical treatments. But in order to shift landscape level trends in wildfire behavior and activity, tripling the current levels may be necessary. So in short, treatment works not only at the stand level, but also at the landscape level, and we need more prescribed fire. And with that, I'd like to say thank you so much, and I'm happy to take any questions.
Great. Thank you, Brooke. That was really interesting. I appreciate you coming on today and telling us about your dissertation work. We already have a question, actually, so I'll just dive right into the questions. And others, please feel free to start thinking and typing your questions into the chat box. So we have a question that asks, in the study, what are the parameters for defining a fire and fire frequency?
So I'm not quite sure how to answer the question, how to define a fire, except that I'm not sure if you mean the difference between a prescribed fire and a wildfire. But I will say that that wildfire and prescribed fire are treated differently in the model. And so when I'm giving these numbers, I am only referring to wildfire metrics, not to metrics with prescribed fire. To parameterize fire in the model, I used the last 15 years of data in order to look at the average annual area burned as well as fire sizes, using just the last 15 years so that I could most accurately represent what conditions are right now. And I'm sorry, Carrie, what was the second part of the question?
The second part, it asked about the parameters for defining fire frequency.
Fire frequency.
Oh, wait, I'm sorry, Brooke, we've got a clarification on that question. So clarification, size of fire, how fuel treatments result in fewer fires, etc., if that helps.
So the data that I used were data from real fires that happened on the landscape within the last 15 years. And as far as the effect of fuel treatments on reducing those fires, that is actually an emergent property within the model that takes into account the fuel beds that are there, the modification to those fuel beds based on the treatment, and then simulated wildfires that are based on a distribution of probabilities for ignition across the landscape. And so the model is calibrated using this historical data to ensure that it is simulating wildfires at the beginning of the simulations that are very close to the fires that have happened within the recent past. But then future fire occurrence and as well as frequency and severity are all emergent, and that is accomplished through interactions between the forest dynamics that are happening, which then changes fuel beds, and also climate, which is interacting with both fire and with forest dynamics. I hope that answers the question.
Great. Another question for you, Brooke. Have you looked at the dollar cost of increased treatment versus the cost savings from the reduction of wildfire?
Oh, that's a great question. So that was outside the scope of this study. I think that's a really important follow-up, though. I do know that prescribed fire is much cheaper than mechanical treatments. So for instance, increasing the amount of prescribed fire on the landscape would certainly be much cheaper than increasing the amount of mechanical treatments. And I think another area for exploration is to look into the reduced costs associated with consolidating treatments in a smaller area because of the smaller amount of road networks that would need to be maintained, and being able to use, the same landings for more than one project, et cetera. So I think the economic side of that is another really important question, but not one that I've looked into in this study.
Great. Well, I wait for other questions to come in. Oh, here's a question. Can you say something more about how the model represents a certain target for prescribed burning? Are you just adding more ignitions to meet those targets, or are you bounding the areas burned in some way?
So for prescribed fire specifically, within the model, I treat it as a management action. And so within the model, I'm able to define management areas that are bounded. Well, I actually used the stands that are already established by the Forest Service. And then in areas where I didn't have data for stands that are already established, I created stands that were of a similar size distribution. And then, yes, I can target specific areas with predetermined fuel types. So I can say, for instance, I'd like to harvest in these, or I'd like to prescribe burn in these particular areas on the landscape, but I want them to primarily have small diameter fuels, for instance, of these particular species. So yeah, you can get very, very specific in how you want to affect prescribed burning on the landscape.
Great. Brooke, drier forests and juniper woodlands that are treated can result in invasive or invasion by invasive annual grasses that then can provide fuel continuity and create yet another problem. Does your analysis account for this? And if not, the results might not hold in the real world.
Yeah, that's a really, really good question. So I did try to account for that as much as I possibly could in the model by including annual grasses as a fuel source. And so I have areas of the landscape that are primarily native bunch grasses where the fire is much less likely to spread at high rates, and then areas that are encroached by annual grasses that are much more flammable, and I've characterized that fuel as very continuous and able to carry fire. So yes, I will say that the model is much better calibrated for tree species and to some degree shrubs. So in my model, in my modeling, annual grasses and native grasses are treated as a fuel type. But yes, I think that is a limitation of this study, where competition between, say, for instance, annual grasses and regeneration of trees may not be completely represented. But yeah, I have tried to represent that as much as possible by including them as a fuel source that is able to regenerate and is especially prevalent in those juniper woodlands.
Brooke, will this information be used in current or future planning in the area? How may the multi-stakeholders respond to these results?
Oh, thank you for that question. I think that this research is another piece of evidence that shows that treatment is something that is important. And it illustrates that the idea of leaving forests to reset themselves is not as successful as actively managing forests. We're in a situation where we've had an effect on these forested areas for well, for centuries, if you go back beyond Euro-American settlements, but specifically fire suppression, cattle grazing, timber harvest, all of these things have had an effect on these forests and the way that fire is interacting with them. And I think that what this study does is it gives another piece of evidence to say that not only at the stand scale, but at the landscape scale, management is important. And mechanical removal of fuels is important, and prescribed fire is also important. And so what managers choose to do with this information, I think, is really up to them. But I think that the evidence presented should be fairly clear to multiple stakeholders that while we might have different stakeholders may have different objectives, the outcome of lowered wildfire activity is beneficial to everyone.
Okay. When you suggest optimal treatment on the landscape where future fire will occur, much of the rest of the landscape will still need to be treated for reducing moisture stress, disease, insects, etc. Are you saying that we would not need to prescribe burn those treatments?
Absolutely not. I think that one of the major takeaways that I had from this research was that even though optimizing spatial treatment for some of the more aggressive mechanical removals could result in reduction of overall landscape wildfire severity and spread, prescribed fire is most beneficial when it is applied across the entire landscape. The results were pretty striking that distributing that prescribed fire across the landscape was more effective than consolidating it in that smaller portion of the landscape. So I don't think that's the case, and I also think that there are management actions that are not for the purpose of fuel reduction. So restoration type treatments or treating areas for reasons other than fuel treatments would certainly need to be considered at a larger area of the landscape.
Brooke, what if the optimized models are overlaid with roadless/wilderness objectives?
I'm interpreting that question to ask if we treated in wilderness and roadless areas, if that would have an effect. And I think that's a good question. There was a study, I believe it was Alan Ager, who put out a study looking at the transmission of wildfire from wilderness areas that are not able to be treated into the surrounding areas. And the results of that study did not show that the restriction against treating in wilderness had an effect on the overall landscape level spread of those fires. But I have heard from a lot of people that there's concern about wilderness areas and roadless areas, and that increasing treatment is an objective held by some. So I think, as far as this part of this study is concerned, I didn't look at that, but that would certainly be a question for future research.
This might be more, excuse me, a comment than a question, but the same person who asked that says, with a lot of timber treatments, slashes left on the slopes for soil stabilization. Let's see if there's any questions.
Yeah, and I was able, that's one thing that with Landis, I was able to differentiate between fuel beds that were resulting from harvest versus fuel beds resulting from prescribed fire or even following a wildfire. And so, yeah, that is one thing that we're able to take into account in looking at future wildfire behavior after treatments. Yep.
Okay. Private timber groups are okay to clear cut, do whatever they want with their land. Could we use this data to suggest that there be some regulation requirements of private companies to employ treatments?
No, I don't know that the results of this study specifically could be used in that way. One reason is because I assumed the same level of treatment in private lands under the optimized scenario and the distributed scenario. I didn't make any changes to that. So I don't think that these results would speak specifically to private landowners. One thing that I do think is an outcome of this study is that the need for increased prescribed fire leads to the need for increased education about prescribed fire, because there are concerns in the public about prescribed fire and the chances of that prescribed fire escaping, or because of the smoke that it causes. So I do think that increased prescribed fire on public lands could certainly be a topic of conversation, but I do think that education about that with the public would be important.
Definitely. Brooke, with the riparian scenario, what buffer rules were used and what % of the landscape was in riparian areas?
Oh, yeah. Well, I would have to look up that exact number, but it was quite small, much less than 1% of the landscape. And because I was working at a 4-hectare resolution, this is one reason why I think that the riparian results were not significant. Because I had to average conditions across 4-hectare sites on the landscape, and so riparian areas, the buffers are variable, but none of them are 4 hectares in size. And so when I averaged conditions for riparian areas, I ended up with such a small proportion of the landscape, like I said, much less than 1%, that my conclusion from that is that treatments in riparian areas are likely to be effective at the stand scale, but on a landscape of this size, I at least was not able to detect that difference.
Okay. Brooke, do the optimized treatment zones have consistent landscape characteristics? What was driving the selection of optimized treatment locations?
So I did not use forest type or elevation as reasons to include or not include areas. But what I did was looked at how frequently fire occurred when there was no treatment on the landscape. So in some cases, those areas ended up being in the higher elevation zones. However, one interesting outcome from this research that I didn't touch on is when looking at forest succession over the next century, those high elevation species are likely to decline to the point of not being on the landscape in great numbers. So there is the probability that some of those high elevation areas, due to climate change, will be transformed from those high elevation species that have a different relationship with fire into more grand fir and into more ponderosa pine. So I didn't disclude them, even though, typically we might not place the same kind of treatments in high elevation forest. But over time, it might not be forested with the same complement of species, and so I left those in as possible areas for treatment. That being said, a lot of those high elevation areas are part of the wilderness areas, and so they were not included in optimized treatment anyhow.
Okay, thanks for that, Brooke. Well, we have time maybe for one more quick question. And while I wait for that question to come in, I'll just again thank you, Brooke, for talking with us about the results of your dissertation work. Very interesting. And I also want to thank you all for taking time out of your busy schedules to listen in today. We do have one more question that came in. Oh, and it's just a thank you to Brooke.
Oh, thank you. Well, thank you very much, Carrie, and thank you all so much for coming. I'm really excited to have the chance to talk to you. And if you have any other questions, I'm sorry, I should have put my email address on the slide, but it's brooke.a.castle@gmail.com. Please feel free to send me any additional questions or comments, or if you just want to chat about fire and forest management, I am into it.
Awesome. Thank you so much, Brooke.
Great. Thank you.
Thanks, everybody. Have a great day.